So, today I want to spend just a couple of minutes summarizing carbohydrate metabolism from start to finish. And then we're going to move on to one last chapter of chemistry, where we're going to introduce some wild new carbon-carbon bond forming reactions, and you're going to learn some interesting things about transition metals that you didn't know before. Before we do that, let's just remember where we've been. Glucose goes through glycolysis to two molecules of pyruvate. And along the way, I've illustrated in blue for NADH and then in yellow or orange for ATP, the energy-rich molecules that we make as part of this process. Glycolysis gives you two NADHs overall. Now those, you're going to learn this in biochemistry and not in this class in any detail. NADH delivers a hydride to a metal center in the electron transport chain in mitochondria. Those electrons get transferred down and ultimately reduce oxygen to water. That is the oxygen you're breathing. The hydrogen gets transported across the mitochondrial membrane to create what's called a proton gradient, and that drives ATP synthesis through a process you will learn about. But in general, measurements have suggested that every one molecule of NADH results in 2.5 molecules of ATP synthesized. That's the general yield. So that's why I've converted NADH into 2 NADHs into 5 ATPs. There's a weird sound. Is that just happens in the MARB? It is the ghost of MARB 222. Nice. All right. Woo. What note is that? Okay. Right. So 7 ATP overall from glycolysis. Then the pyruvate dehydrogenase complex converts pyruvate into 2 molecules of acetyl-CoA and 2 molecules of CO2. That's what you're breathing out. Along the way, we make 2 NADHs, which get converted into 5 ATP. And then as you learned that last time, the citric acid cycle, why have I never noticed that before now? Has that been going on the whole time? You're Miriam, you're gaslighting me. It's not been going on the whole time. All right. Anyway, I'll try not to be distracted. You learned last time that the citric acid cycle takes acetyl-CoA, oxidizes all of the carbons in it to CO2, and in the process we get, for every 2 molecules, and again we're balancing this relative to glucose, glucose leads to 2 molecules of pyruvate. It went away. Now that's distracting. Could somebody out there just go, woo? Thank you. That's better. Yeah, go ahead. For every 2 molecules of acetyl-CoA, we get 6 of NADH and 2 of FADH2, and then 2 GTPs. The uses of GTP are slightly different in the cell than ATP. We won't talk about that. You'll have to learn about that in biochemistry, but they're readily converted into ATP, so we're going to count them. And then here's the conversion of 6 NADHs into 15 ATP. FADH2 is a slightly different hydride carrier. It delivers hydride to the electron transport chain at a different spot. And so every hydride delivered from FADH2 generates fewer equivalents of ATP, drives the proton gradient a little bit less. So it's estimated about 1.5 ATP per FADH2. Put it all together and you get 32 ATP from the complete metabolism of each glucose. And that ultimately, if you follow through, oxidizes all 6 carbons of glucose to CO2, and that's what you're breathing out, okay? And again, the oxygen that you breathe in is tied to this process indirectly. Oxygen accepts the electrons that are delivered to the electron transport chain. Yeah? Was I recording? Yes. And we're getting audio. The bigger question is, did the audio pick up the mysterious ghost of MARB 222 sound? And I don't know about that. Yeah?
So that was after we invested 2 ATP?
That's counting the 2 that we invested. So this is the net overall yield. Okay. So if you can start to do a little bit of math, this is kind of interesting to think about. It gives you a sense for the sheer scale and quickness of this chemistry going on inside your body. Assume the average human about your age needs about 2,000 calories a day. By the way, the calorie, capital C, on all the food products is a kilocalorie, kcal. So you need about that much energy every day to stay alive, to move and to do what you need to do. The average change in free energy for ATP hydrolysis, this depends on the source, whether you're dealing with standard conditions or actually conditions inside the cell. So I've given you a range of values, but it's on the order of 7 to 15 kilocalories per mole. So from that, you can figure out how many moles of ATP do you need to hydrolyze every day or use every day to stay alive, and therefore how many moles of ATP you need to generate. So you do the math, and you need somewhere between 130 to 300 moles of ATP every day. Now that's, you know what a mole is, right? 10 to the 26, roughly, molecules. So that's an astounding number of ATP molecules. That ends up being 66 to 152 kilograms of ATP. Now, let's put that in perspective. Average human weighs maybe in the 80s kilograms, and average, there's a plus or minus. I'm obviously on the plus side of the standard deviation. But you don't actually have that many kilograms. There's a lot more in your body than just ATP, right? You don't have that much ATP in your body. That's what you need to use every day. So obviously you're recycling ATP. Now, how much ATP do you actually have, and how many times does it get recycled in a day? We can figure that out. The math's a little bit sketchy. And you can back calculate based on this number about how many grams of glucose, if you wanted to subsist on just glucose alone, would you need. And it's 1.5 kilograms, maybe about a kilogram of glucose. You could eat that. It doesn't taste very good. Glucose doesn't taste as sweet as sucrose. How much ATP is in an average human? Well, the average concentration inside the cell is about 3 millimoles per liter of ATP, or 0.003 molar. What is the average volume of a human? This is something I hadn't thought about. How much liquid does a human have in them? About 42 liters, give or take. More now. So you can do the math. This is general chemistry dimensional analysis. Are you so excited about this? Is this going to be on the test? No. 126 to 168 millimoles of ATP. That's what you have, but you need to generate 300 moles, which means that you recycle every molecule of ATP anywhere between 1,000 to 2,000 times every day. Every single day. So that's going on as you breathe. That's that's accepting electrons that you've generated. That's driving a proton gradient. That's synthesizing ATP. The electrons you get by oxidizing glucose down to CO2 through this process that we've talked about. All of it going along at a blindingly fast pace, faster than you can comprehend. It's kind of crazy. And all of this, when someone tells you need to go burn some calories, it sounds like horrible, but this is the amazing stuff that's going on when that happens. And everything, thinking, sleeping, everything requires it. So it's an amazing thing. All right, that concludes metabolism. So you'll learn so much more in biochemistry about the way the systems are related to each other, more from people who know more about it than I do. So look forward to that. Now we're going to continue onward with some chemistry. So if I were to choose a title for chapter 28, your book's title is Carbon-Carbon Bond-Forming Reactions in Organic Synthesis. But what we could call it is Nobel Prize-winning reactions that involve transition metals. And this is going to enable synthesis of things that you haven't been able to do before. So what I thought I would do, since many of you are concerned about this at this time of year, is do a quick overview of all of the or most anyway, all that I could think of, the carbon-carbon bond-forming reactions that we've learned how to do. Carbon-carbon bonds are important because they allow you to build up structure and complexity. And they allow you as a chemist to do things that the biologist would like to do. So a biologist might say, make me a molecule that does this. And ultimately that's going to come down to a synthetic chemist actually putting the atoms together. So here are the tools we've got so far. If you remember from very early on in the course, you could take an aldehyde or a ketone and do organometallic reagents like an organolithium reagent or or a Grignard reagent, and the new bond that you make there is usually a bond between in the end, two sp3 hybridized carbons. That's just addition to a carbonyl. Does that sound familiar? If it doesn't, what does Alma say? I would that ye should repent speedily, for such an one is not prepared. Yeah. All right. You've learned how to do some other things with, say, an ester in an organolithium reagent or a Grignard reagent. In this case, you'd make a tertiary alcohol. But again, the two new bonds that you make are bonds between sp3 hybridized carbons. Let's see. Also, there was conjugate addition. Do you remember when you used a cuprate? You could add the R group to the beta carbon of an alpha beta unsaturated carbonyl compound. I've messed it up. Whoops. Sorry. You could add whatever the R group is to the beta carbon of an alpha beta unsaturated carbonyl compound. And again, the bond that you make is between sp3 carbons. And in fact, a lot of the bonds that we have learned how to make are of this kind. Do you recall enolate alkylation? That sound vaguely familiar? Do you remember how we would take something like this? We would use LDA to make an enolate, and then we would add some kind of alkyl halide, again, usually a primary alkyl halide, and we would make a new bond between the alpha carbon of the alkyl halide, the alpha carbon of the carbonyl compound, and then whatever this R group is, it was. And again, this is usually a bond between sp3 hybridized carbons. So we got a lot of ways to do that. Addition to carbonyls, and then we've got enolate alkylation. Okay, and there were others that generated similar bonds too. For example, if you recall the aldol reaction, there you would start with, say, a ketone, and you would use a weak base. You'd make a small amount of enolate, and then one enolate would attack the other carbonyl compound. You would make this new bond between the alpha carbon of the carbonyl compound and then the carbonyl carbon of another one. And again, that new bond that you made is a bond between sp3 carbons. Though if you do the dehydration step afterwards, you've known that you could also make both the sigma and the pi bonds. Okay, so that was the aldol reaction, and there's some other versions of that. For example, I won't illustrate it, but we talked about the Claisen, which was a similar way to make a new bond. In the Claisen, well, I won't do the mechanism, but we can sure write it down briefly. In the Claisen reaction, we would take an ester with a base, and the product of the Claisen reaction would be a beta keto ester. And there, again, the new bond you make here, it's no longer a bond between both sp3 carbons. It's a bond between an sp3 on the right and an sp2 on the left. Okay? So, and I taught you this earlier, that you should get good at looking at products and thinking about what bonds in those products do I know how to make via various processes. And there are more that we could talk about. I won't give you a comprehensive list because it's worth you going back and figuring out what those items are, but they're all embedded in the study guides and the practice exams. Maybe better would be to show you some bonds that we don't really yet know how to make. Okay? So let me give you an example. Suppose you wanted to make a bond in a molecule that had, you wanted to make a bond between two benzene rings. Suppose this was the molecule you wanted to make. We've done stuff with benzene rings before, but never that kind of thing. The best we could do with a benzene ring prior to this was, say, to make a carbon-carbon bond was with a benzene ring, was to do a Friedel-Crafts reaction, where we could make a bond between the benzene ring. That's an sp2 carbon, but a lot of organic chemists, it's not the same as a typical sp2 carbon. We'll call that an aryl carbon, or AR. So this is a bond between an aryl carbon and an sp3 carbon. So we've done that before, and that's Friedel-Crafts alkylation. You could use an acid chloride and do Friedel-Crafts acylation, and that's a similar kind of bond between an aryl carbon and, in this case, an sp2 carbon. But we've never, ever done that with a benzene ring. Can you think of a reason why it would not work to do a Friedel-Crafts reaction, say a Friedel-Crafts alkylation with a benzene ring? What do you remember from the mechanism of the Friedel-Crafts reaction? In the case of the primary alkyl halide, you first activated the leaving group, and then the benzene ring did SN2 type chemistry with backside attack. Alternatively, if you were using a tertiary alkyl halide, the leaving group would leave first, and then you would form a carbocation. That was a previous mechanistic exam question that some of you got wrong, and that detail is probably worth some review. Why is that not a reasonable intermediate for the benzene ring? You learned that way back in 351, right? Do we ever have a leaving group leave from a benzene ring? Let's even put the activating Lewis acid on it. Do we ever have a leaving group leave from a benzene ring to give a localized positive charge? No. And that's been an exam question before too, where that was an unreasonable intermediate. Actually, that was a question about which molecule reacts fastest in an SN1 reaction. And you had to draw this carbocation and realize that we have never ever suggested that an sp2 carbocation that's not resonance stabilized is a good intermediate. In fact, it is prohibitively, I already started, so now I have to finish, prohibitively unstable. So you can't use Friedel-Crafts chemistry to make this bond. We need an alternative method. And another example that's related to a similar idea is, what if you wanted to make derivatives of benzene that look like this? What if you wanted to make this bond between a benzene carbon, an aryl carbon, and an sp2 carbon that's involved in an alkene? There were ways we could do this. You could do the Friedel-Crafts reaction first, and then after you had the alkene, maybe you could do the radical halogenation and then form the alkene by elimination. But what if we wanted to make it directly? Again, it's got a similar problem. If you tried to do a Friedel-Crafts reaction on an alkyl halide with an alkene in it, you'd end up having to go through a carbocation intermediate that's too unstable. So we need some alternative methods. So we want to introduce the possibility of some of these alternative methods, and they're going to involve transition metals. In each of these reactions, I'm going to show you the reaction. Then we're going to talk about, and that it works. Then we're going to investigate mechanism. And as we investigate mechanism, we're going to have to learn some things that you probably don't already know about transition metals and that I only barely know. If you want to know more about this, you can take some classes in the chemistry department. My colleagues, Dr. S. and Dr. Michaelis, are really good at this sort of thing. Okay? All right, so let's start with a particular reaction involving an alkyl halide and a cuprate. And this time it's going to be a benzene ring cuprate. So cuprates have two R groups attached to the benzene ring. The copper is in the +1 oxidation state, It's got a negative charge on it when it's bonded to two things, and lithium's the counter ion. We're going to have more to say later on about this reagent. This is a new reaction that you have not seen a cuprate do before. But if you bring the cuprate in with the alkyl halide, you can make a new bond between the benzene ring of one of the R groups on the cuprate. Here's the new bond in red. And then this, let's just label it pink, will be the carbon that had the leaving group on it. And you've made that new bond. Now, okay, at this point, we still aren't solving our problem because this is something we could have made through the Friedel-Crafts reaction, but we're going to illustrate something interesting about transition metals and how they do things. Propose a mechanistic hypothesis. What do you think is going on here? Do you think somebody's attacking who? Who do you think is the nucleophile? This is based on your previous experience with cuprates. You think the negatively charged cuprate's the nucleophile, right? We've seen cuprates do things like this, where basically the carbanion acts as a nucleophile, leaves from copper, and then attacks an electrophile. So propose a mechanistic hypothesis here. What do you think is happening? Where do you want me to draw my arrow? I'll start it from there. You're proposing SN2 chemistry, right? That seems reasonable. And bromide leaves, okay? That's an interesting hypothesis. If your hypothesis is correct, then let's try some other experiments to see whether those experiments are consistent, the results of those experiments are consistent with your hypothesis. So, if the mechanism was SN2, what do you predict for this? Dun, dun, dun. Gotta wait for it. You got to move down the page. Some of our students don't like it when we have writing that spans the page because the PDF doesn't look nice. So, all right, I got you, friend. So let's change things. Let's let the benzene ring be here with the leaving group, and then let's let the 4-carbon chain be on the cuprate. Now, if the mechanism is SN2, what do you predict for that? Is it going to work? Shouldn't. Why? Well, you memorized that we don't do SN2 at aryl or sp2 hybridized carbons. One reason for that is SN2 proceeds with backside attack. You got to get to that anti-bonding orbital that's 180 degrees away from the bond. That orbital is sticking right in the middle of the benzene ring. There's no way you're getting to it. Sterics prevent that. You can't get to the right place. So if the reaction was SN2, you predict no reaction. In reality, what actually happens? You make the bond and the molecule says, what's the big deal? It's fine. So, conclusion, mechanism is not SN2. It's more complicated. Okay? Now, hold that in your mind. I will show you the mechanism, but you need to learn some things about copper and other transition metals before we get there. So we're going to take a step back to learn some things about chemistry of transition metals. Now, we don't have a periodic table here in the room, so I'm going to write out portions of them, portions of the periodic table here. I know these because I used to sometimes occasionally still play a game on my phone called Atomus, where you have to combine various atoms together and then you make other atoms, and it's kind of fun and a time waster. But I know some of the transition metals now. Scandium, titanium, vanadium, chromium. Across the top, we're going to write number of valence electrons. Okay? Manganese, iron, cobalt, nickel, copper, and zinc. Okay? And the number of valence electrons increases as we go from left to right. Okay? Just for your general edification, the transition metals that are on the left-hand side are called early transition metals. The ones that are on the right-hand side are sometimes called late transition metals. The ones on the left, and it will depend on what oxidation state they're at, but you can generally think of the ones on the left as being electron poor. That's probably obvious because they have fewer electrons, right? The ones on the right you can think of as being electron rich. Now there are some other, there's tons more transition metals. I've just shown you the first row. I'm going to fill in a few other common metals in columns, and of course if you were to take an exam for me, as you know, the periodic table is provided. So cobalt, ruthenium, osmium all have, oh no, that's not cobalt, that's iron. There we go. One row down from iron is ruthenium, one row down from ruthenium is osmium, one row down from cobalt is rhodium, RH, and one row down from rhodium is iridium. One row down from nickel is palladium. That's a big important one that we'll do a lot of chemistry with. One row down from palladium is platinum. And again, there's a lot that we're not filling in, and you'll have all of this, but the most important thing for our discussion today is just you'll need to know how many valence electrons a transition metal normally comes with. If you don't need to memorize it, if you can figure it out by looking at a periodic table, that's not going to add too much time to your process. All right. Now let's start looking at some what we're going to call organometallic complexes. These are molecules in which metals are bonded to carbons. Organometallic complexes. As you can see, the cuprate is one such organometallic complex. You've got a copper bonded to two things, okay? So we'll actually look at that here. Here is copper. It's bonded to two things. One important thing you need to know about transition metal complexes is that it is when people draw transition metal complexes, it is not customary to show formal charge on any individual atom. Now we've done that religiously since the start of 351, and it's been really important to us. But when it comes to transition metal complexes, there is a different way that works better for keeping track of electrons. And remember that formal charge was just a way of counting electrons anyway. So one thing people will do is just indicate in what they write on the paper the overall charge on the molecule. That's sort of half a little bit of a bracket. You know that the overall charge on the molecule is -1, okay? This in pink is the metal, obviously. And then in orange are going to be, oops, I'll highlight in orange, are the ligands, okay? So ligand is something that binds the metal. And we're going to see that there are two kinds of ligands that can be bound to metals. This is going to sound a little bit like Pokemon language here, which is weird. Like, I don't know if any of you were ever into that. My kids were. I never was. But you get a new card, and oh, this is an ice-type Pokemon. Ooh, ice. Well, this is a dirt-type Pokemon, or earth, or whatever it's called. This is a fire-type. Dad, that's Mega Rayquaza. Are these? I missed my calling in life. I apparently could have made some money by just making up words and then drawing something and then attaching interesting properties to it. So anyway.
What you're doing right now.
It's what I'm doing right now, right? Everything. I've been gaslighting you all of this is just made up, right? Right. So, introducing the X-type ligand versus the L-type ligand. Now, we're not going to use L in the terms that your generation does. I was informed by the teachers' quorum that I advised. They were over at the house. We were baking Christmas cookies, and I was asking them, like I've asked you before, about the use of the term Riz. And they said, yeah, Eli over there, if you look up Riz, his picture's next to it, but it says L Riz for him, but it says W Riz for me, was the kid talking. So I inferred from that L is loser. And anyway, no, that's not what this means here. An X-type ligand, so when you see an organometallic complex, you assume that the electrons in the metal ligand or metal X-type ligand bond go with the ligand. They belong to the ligand. Go with is shorter than belong to, so hopefully you can deal with that. What I mean by that is when X-type ligands leave, they leave as X minus, or if you conceptually pulled them away, they leave as X minus. When L-type ligands leave, they leave as neutral, okay? So just imagine in your mind the R group here leaving with its electrons. We're not saying that it does, we're just thinking about it. If the R group here left with the two electrons that are in the bond between the carbon and the metal, that R group would be negatively charged. Can you see that? That's an X-type ligand. Okay, let me show you a different molecule, a different organometallic complex. This is going to involve palladium, and it's got 4 bonds between palladium and a molecule that's called triphenylphosphine. Now, remember, in organometallic complexes, we do not worry about or show formal charge on any individual atoms. That's not something that's been allowed before. If you look at that, you'd say, okay, what is triphenylphosphine? Well, it's a phosphorus bonded to 3 phenyl groups. Phosphorus is from the same column of the periodic table as nitrogen. Normally, you would think if the phosphorus is bonded to 4 things, it should have a positive formal charge, right? I agree with you. Nobody cares. Nobody draws it that way. All right? So you're just going to have to deal with it. The way you deal with it is you notice that the overall charge on the molecule, because it's not indicated, is neutral. Then you see, okay, if I pulled phosphorus away from palladium, if I conceptually did this in my mind, what would it leave as? It would leave as the neutral, can't spell neutral, it would leave as neutral triphenylphosphine. So the R group up here is an X-type ligand. The triphenylphosphine is an L-type ligand because it leaves as a neutral ligand. Okay? So what are some examples of ligands that might be X-type ligands? Basically anything that you can think of that might be negatively charged. So hydroxide could be an L-type ligand, an X-type ligand. Any of the halides, chlorine, bromine, iodide, fluorine, a carbanion, basically any negatively charged carbon, hydride, a bond between a metal and hydrogen, that would be an X-type ligand. Anything you can think of that might be negatively charged, okay? Negatively charged nitrogens can sometimes be ligands on metals or can be X-type ligands, okay? And again, we're not thinking of we're thinking about what the charge would be if the ligand picked up and left with the electrons that are in the metal ligand bond. Common L-type ligands is basically anything you could think of that could bind a metal and be neutral while doing so. So for example, water could be an L-type ligand. An amino group could be an L-type ligand. A phosphine, basically anything that's neutral with a lone pair of electrons, including sometimes carbonyl oxygen lone pairs. Also including, and this is kind of crazy, but it works, alkenes. The pi electrons of an alkene can be an L-type ligand, though how you draw that is a little bit tricky, and we won't worry about that in a lot of detail. Okay, L-type ligands, X-type ligands. Questions about that? I understand we're weaving a lot of lines of the story here, but we're going to get there. Go ahead.
So if both of the lone pair electrons come from the ligand, would that mean it forms a coordinate bond with the transition metal?
Right, so for the most part, we're going to assume, and if you've learned some stuff from general chemistry, yeah, the ligand, the bonds between the metal and the ligand usually come from, or are counted as though they come from the ligand. We're going to see cases where they come from the metal, but as soon as they make the bond, they count as though they're bonded to the ligand. Yeah. Okay, yes?
Just going over the definition, I guess, between X-type and L-type. So X-type, if it leaves as a negatively charged molecule,
Yep.
it's going to be an X-type, and then L-type if it leaves as a neutral.
Exactly. X-type is it leaves as negatively charged. L-type is it leaves as neutral. Yes?
So if you get like a copper with a 7 minus, is that usually
Okay. Copper?
is that usually
That's not a 7, that's a bracket. Yeah. So, sorry, that's not a 7, that's the whole complex is negatively charged.
yeah, I thought I heard you say 1, but then I thought
Yeah. Yep, just one negative charge overall. Sorry about that. Okay. So now, yeah, go ahead.
So how come it's just one negative charge instead of two? Because like there would be two negative ligands.
Right. So now you're right. There's two X-type ligands, but the overall charge on the complex is just 1 minus. That's going to tell us something about the metal. We're gonna account for everything by adjusting the charge on the metal to give us the correct overall charge on the molecule. Right? Yeah.
perhaps this is like a bit wrong, but in PPH3, the Wittig reaction, it has a charge.
Right. When we did the Wittig reaction, we used formal charge, and that's the Wittig reaction didn't involve metals. We were using our standard rules. Yep. And you just have to be comfortable with two different ways of counting electrons. We're not cheating. We're not breaking any science. We're just dealing with how we count the electrons differently. All right. So let's see how that works out in the case of the cuprate, right? The overall charge on the complex, I'll just bring that down here. We've already said that the two ligands are X-type ligands, right? The overall charge on the complex is what? -1, right? What about the overall charge from ligands? So, therefore, the charge on the metal must be what? To balance it all out, has to be +1, right? So that tells me that this complex involves two of these X-type ligands, right? And it involves copper, and the copper should be in the +1 state, okay? You have just learned how to identify the oxidation state of copper, okay? You take the overall charge on the complex, you compare that to the charges on the ligands, and from that you can infer what the oxidation state of the metal is, okay? All right. Now, there's two other things you want to know about transition metal complexes. One is how many d electrons the metal has. That can sometimes give you a sense for whether a reaction is reasonable or not. And in reactions for whether a metal is electron rich or electron poor, and in reactions where a metal is going to use a pair of electrons to do chemistry, you want to make sure you know that a pair of electrons is available. Because it is not customary to draw lone pairs on metals, right? So normally when we've drawn like the structure of water, if we wanted to remind ourselves that the oxygen had 2 lone pairs, we'd just do that. There's enough d electrons on metals that it is no longer customary to draw little dots for lone pairs. You sort of run out of space. So instead, you got to keep track of it, and this is how we keep track of it. So to figure out how many d electrons, what you do is you compare the number of valence electrons that copper normally has, and then you adjust it for the oxidation state. So copper normally has, from our periodic table, we would see copper normally has how many? 11? Well, let's see. Is that right? Sorry. Copper has 11 valence electrons. So one of the things you learned is the 4s orbital gets filled before the d orbitals, so you're not counting those 2. But once a metal is in a transition metal complex, you count all of those, both the 4s orbital electrons and the d electrons as being available. Okay? That's annoying, but it's true. So we're going to say that copper has 11 valence electrons because it's in the 11th row of the column of the periodic table. And its oxidation state is 1, it's +1, so we're going to subtract the oxidation state from the number of valence electrons, and we determine that this copper has 10 valence electrons. And we're going to say they are all in the d orbital, so that's a d10 metal. Now, I know that I'm glossing over something. I know some of you don't buy that I can use the 2 4s electrons. I'm sorry about that. When you put a metal in a complex, it changes the relative energy levels. The d orbitals are more available for bonding. That can lead to lower energy. So you'll have to take my word on it. I actually can't convince you that it's true anyway, because I'm not sure about all of the details. But we would say that this copper complex is a d10 complex, meaning it's filled up its d orbitals, which means this is pretty electron rich as a complex. That's useful because now you have an idea if it's electron rich, it's probably a decent nucleophile. Okay, the other thing you want to know is, in addition to how many d electrons, what is the total electron count in the complex? So to do this, we count the d electrons. There's a C in there, you just can't see it. Plus, sorry, dang it, I ran out of space, shoot. You count, for the total electrons, you count the d electrons plus the electrons in the metal ligand bond. And the idea here is we're dealing with what we could call an expanded octet rule. Do you remember the octet rule for the second row elements comes from the fact that we only have 8 spaces, right? Only 8 places for electrons to go. When we're in the transition metals, we've got not only the 4s orbitals and the whatever level 3p, 4p orbitals to fill, but also the 3d orbitals. So instead of only having 8 electrons, a transition metal can potentially be surrounded by 18. Okay? So our limit for a transition metal complex is 18. That's our new octet rule. So let's see how copper keeps this rule. It's a D10 complex, and then how many electrons are in metal ligand bonds? 10. Let's see. No, not 10. That's how many are the D electrons. How many metal ligand bonds do I have? 2, right? So I have 4 electrons, 2 electrons in each metal ligand bond. Overall, this is a 14 electron complex. Now that's important because that tells you over in the analogy here is that if I ever drew before a carbocation like this, you would say, aha, empty p orbital, a place for a nucleophile to attack. That carbon is electron poor. There's a place for another bond to be. If you know that this cuprate complex has 14 electrons, you know that there's a space for 2 more things to bind if you had them. Okay? That's important. You don't have that insight unless you do this analysis. Okay? So let's now, we're going to don't worry, because we're going to go through quite a few examples in the near future about assigning metal oxidation state, counting d electrons, and then counting total number of electrons. But for now, let me show you how this works out in the mechanism for the cuprate reaction that I just showed you. Okay? So all you know from this is that there is no SN2 reaction. I mean, there is, but not for this copper, right? Did I just scare some of you? Okay, all you know is that I can make this bond, but the reaction is not SN2. All right, so let's view how this works, and I'm going to erase some things. I'm going to redraw copper with the little bracket and the negative charge. You know here that copper is a D10 metal, and you know that it has 14 total electrons surrounding the metal, so you know there's a space for more stuff. All right? So what's thought to happen here, and I don't have time to illustrate it today, though I will illustrate it next time, is that 2 things happen at once. You form a new bond between copper and the halide at the same time as you form a new bond between the carbon and the copper. That's a different thing than you've ever seen before. Normally, you've seen 1 pair of electrons attack and form a new bond. Here, 2 sets of electrons are changing, right? And a pair of electrons on the metal is becoming a new metal ligand bond. And then the pair of electrons here, this carbon-carbon bond, is also becoming a new metal ligand bond. I've drawn the arrows that way. It would be fine, and you actually cannot tell. There's no experiment that I know of that illustrates this. You cannot tell whether it's this way or that way. You can illustrate it however you want. But those 2 things go on at once. And then what you get after that is the following. You get the 2 4-carbon chains attached to copper, and then you get 2 new things attached to the copper. You get the benzene ring and the halide attached to the copper. Okay? Let's examine what's changed. What's the overall charge on the complex? It's still -1. How many, what ligands do I have? Are they L or X? Think about them as if they left with the electrons in the bond. They are all X-type ligands. So now we have 4 X-type ligands. The overall charge from those ligands is -4. Therefore, what is the charge on the metal? Must be +3. So the metal just got oxidized. Over here, the metal was +1. The oxidation state, it's -1, subtract -4, that's how you get +3. The oxidation state of the metal increased in this process because we took 2 electrons that used to be on the metal, 2 d electrons that used to be on the metal, and then we used them to make a new metal ligand bond. That kind of step is a classic mechanistic step. It's a new one in organometallic chemistry. It is called oxidative addition, and it's where you add something to the metal. Now, we're out of time. I didn't get to finish the story. So, it's Friday. It's a cliffhanger. See if you can focus in church this weekend while you're thinking about this. I know you can't wait. I'll see you Monday.